to Lab 9 of EECS 281. I hope you're all doing well and staying safe. Today we're going to be discussing graphs, search algorithms, and MST algorithms. Just some quick announcements for you. Just pause the video if you want to read through these. Near the end of the semester, we like to kind of do a quick review of classes that come after EECS 281. I can't speak to all of these classes. I've taken EECS 482, 442, 388, about a month and a half of 45 until I couldn't get off the wait list. But I've had a positive experience with all of these. EECS 490 I'm taking right now. Of course, I can't really speak for it with all that's happening right now. But the class did change a lot since last semester, so you should ask someone who took it this semester for advice. But yeah, I found these courses to have a nice breadth. It's important to plan ahead for your EECS courses to figure out how you're going to explore different topics and concepts that you might pursue in your full-time career. So yeah. I do like to do an emoji of the week. This is something I've been doing for the past 2 semesters. They're not always that great of emojis. It's not very high effort, but this week's emoji is the laughing at random virus memes all day emoji. Very funny. Okay, let's keep going. So let's start with graph terminology and ADTs. We'll start with a graph definition that we might have seen in EECS 203, which is essentially that a graph is just a set of vertices and the edges that connect them. So a very simple way to represent this graph right here is by just storing the vertex pairs that make each edge. Right, so all we need to know is that this vertex is connected to this vertex, that V4 is connected to V5, that V5 is connected to V8. And we might store that as pairs, kind of like this. So we might have a pair 1 that says we're connected from 1 to 4, and then we have another pair that says we're connected from 4 to 5. And this is how we might represent our graph. It's all the information we need to reconstruct something like this. Now there are different types of graphs. We might have a directed graph, kind of like in Twitter you might have a connection where you follow someone but they might not follow you back. Yikes. But that would be a directed graph because you could have bi-directional relationships or single directional relationships. On Facebook, right, you can only be someone's friend if they're also your friend, and so it's not directed here in this friendship graph. This is an undirected graph. And we might have an example over here with a road network where we have a weight associated with an edge. So maybe this says that to go from 4 to 5, it costs you 58 work units. It's more difficult with larger edge weights. And so we have weighted edges as well. Some more terminology. A simple path is a sequence of edges leading from one vertex to another with no vertex appearing more than once. And so this is an example of a simple graph. Right, we might go from here to here to here. Right? A simple path takes us through this sequence of edges without having to repeat a vertex. You might remember that game that people would play when they were younger, when they were trying to draw out that box, and there was no way to ever do it without repeating a vertex. So there was no simple path to that. A connected graph is a graph is one that has a path that exists between any 2 vertices. So if I have this set of vertices, it's connected if we have a vertex that allows everything to be indirectly related to everything else. So I can go from this vertex to this vertex by traveling here. It would become disconnected, or it wouldn't be connected if I have a vertex like this that's not connected to anything, or another tree that's like kind of separate. A cycle is when we have a simple path from a vertex to itself with no edge appearing more than once. So here's an example of a cycle. A cycle doesn't have to be just 3 vertices, right? We could have a cycle like this. A sparse graph is a graph with few edges. Now, you can be a little objective about this. We usually say that a dense graph, as opposed to a sparse graph, I should say here, E is approximately or proportionally equal to the square of the number of vertices. We use these variables E and V a lot when we talk about graphs. If there are about V squared many edges, then we have a very dense graph. And so where does this number come from? Again, this might be something you might remember from EECS 203. If we have 4 vertices, the maximum number of edges I could have would involve connecting every vertex to every other vertex. So like this, and there we have approximately v squared many edges, because we've connected as many as possible. So the maximum amount that you can actually have, the maximum number of edges, is such that every vertex v1 is connected to v minus 1 other vertices. So that's approximately v squared. Cost, we've seen with a weighted graph. The weighted graph, it's just the sum of the weights of the edges that we've selected. So we might have a path that goes from here to here to here. So this path right here would be a path of cost 9. In an unweighted graph, we might treat each edge as a weight of 1. So they have an equal weight. The difficulty or the cost associated with going from one vertex to another is just 1, because every traversal from one node to another is the same in weight. So we talked about abstractly representing a graph, but we actually have to consider how we're going to store it in memory. How are we going to actually store and represent this graph in C++ in a way that's appropriate for whatever algorithm that we're writing? And so naturally, there are many ways to do this. With an adjacency list, which we see right here, we have a list for each of our vertices. This represents vertex 1's connections, which says that vertex 1 is connected to vertex 2 and connected to vertex 5. And so I only have as many entries in this list as I have connections to this vertex. So if there's a vertex with nothing connected to it, it would just be an empty. It would be an empty list. With an adjacency matrix, we have an entry for every vertex So let's say we're looking at vertex 1 here. A 1 would represent a connection to the vertex of the corresponding row. So 2, 1 is an edge in this case. But you might notice that the primary difference between these is the fact that you have fewer entries for a vertex if you don't have any connections to that vertex, or we only have as many nodes as we need here. Whereas in the adjacency matrix, even if 5 isn't connected to anything, even if it's all zeros, we still have to store this in memory. So this takes space. But we have the added benefit with an adjacency matrix of random access. So I can always say, oh, what is 4 3 an edge? And if that ends up being 0, then we know quickly, yes, there's no edge between 4 and 3. Whereas if I wanted to check 4 and see, okay, does 4 have a connection to 3, I would have to traverse every single entry, and that could be up to v many entries if I have a dense graph, right? So it can be faster to use an adjacency matrix or an adjacency list, depending on the algorithm that you're using. All right, so let's talk about sparse and dense graphs. Let's look at some examples. Here we have about, let's say, 10 different vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have a very small number of edges. Remember, if we have the number of edges about equal to v squared, in this case it would be around equal to 100, since we have about 10 vertices here, then we would have a dense graph, but we don't. We have about 10 edges, I think, and so that means that we have a sparse graph, right? We haven't loaded the graph with as many edges as possible, or nearly as many edges as possible. So that's sparse. We also have the internet, right? This is a huge graph with so many different websites. Each kind of little point here represents a website, and each connection represents a relationship between multiple websites through a hyperlink, right? So websites are linked together, but it looks like a huge graph, but does that tell us anything about whether it's sparse or dense? No, the size of the graph doesn't really tell us much. It's about how many edges are there relative to the number of vertices. And if you just think about it, like if you go on like a news article, you see a bunch of links, maybe 4 or 5 links in one article, but you're not going to see on the order of 5 trillion websites linked in that one website. And so because the number of edges on average that each vertex has is far fewer than the number of vertices, E is much, much smaller than v squared. And so this is also going to be a sparse graph. All right, here's another fun one. We have a dictionary such that an edge exists if 2 words start with the same letter. So here are some examples right here. Apple and alligator are part of the same group. They're connected. And this is a more tricky problem in my opinion. So you might think about, okay, how many edges do we have? Is there any way we can put a mathematical kind of representation on this? Let's say that there are, v many words. Let me change the color a bit. This is kind of jarring. So let's say we have all the A's in this cluster, all the B's in this cluster, all the C's, and over here everything is connected to itself, right? So we have, let's say B has B many words, right? We have about B squared many edges just in this group over here. So if we assume that on average there are V over 26, because there are 26 characters, 26 letters in the alphabet, if there are about V over 26 letters, V over 26 words in the A group, how many edges are there if this is a maximum, if everything is fully connected? And it is, because everything in A is adjacent because of this rule. Well, that would mean we have V over 26 squared edges in this section of the dictionary. And we also have V over 26 squared edges in this part of the dictionary. And if we add all of these up, we still end up with an E proportionally equal to V squared. And so this ends up being a dense graph. Alright, so let's get into graph traversal algorithms now. So we've seen depth first search and breadth first search in Project 1. We've used a stack for depth first search and a queue for breadth first search. Before we look at an example, just to refresh your memory, I want to note that when all edges have the same cost, a BFS is giving us the shortest path between nodes. Because the characteristic of a breadth first search is that we're just focusing on breadth. We're just focusing on, let's say this is our graph right here. And I want to get you out of this mentality of thinking of graphs as trees, right? Trees are just one way to represent a graph. They're just a type of graph, but we can have a graph where everything is kind of just randomly spread apart. Let's say we have these kinds of connections here. Breadth first search is looking at the things that are direct neighbors of the vertex that we're in. So we would maybe look at these, and then we would spread out as we go through a breadth first search. And because it's focusing on things that are close to where we began, we are finding the shortest path. And again, this depends on the edges having the same cost or having no cost at all. So because there's this rule, we can't use BFS to just find the best way to go from different locations on a map, because locations on a map have a certain distance involved with their vertices. So depth first search, here's some pseudocode. With DFS, we would be, let's say, starting at this root node of the tree, and we would be adding this direct neighbor from the neighbors of this vertex, and then we would make a recursive call before we actually worry about this neighbor over here. So that means that we do a recursive call DFS on this node, and then once we're done with that, we get out, go all the way back out. We deal with this node, recursive call this node, and so on. With breadth first search, however, we're going to add these neighboring vertices that are direct neighbors of vertex to a queue. So let's say we have, this is 1, 2, 3, and 4. We would be adding 1, and we'd pop 1 out, and now we're going to add its neighbors, 2, 3, and 4. And now we continue on these iterations of BFS by popping 2 out. Why can't I select this? By popping the 2 out and continuing from there. And so we would be kind of covering things based on nearness to where we started. So let's talk about minimum spanning trees. I guess this is the beef of today's lab. So with spanning trees, we have a subset of a graph such that it contains all the vertices in V, where V is the set of all the vertices in the graph. It's connected, which means that no vertex is left out and not connected. And it's acyclic, right? We can't have this cycle over here. This would not be a spanning tree, because a tree cannot have a cycle, right? Who sees a tree outdoors where one of the branches ends up uniting with another branch? I mean, maybe it happens sometimes, but that's not the definition of a tree. So we have a spanning tree, acyclic, everything is included, and it contains all the vertices. Okay. But we have another type of spanning tree, which is a minimum spanning tree, in which we try to reduce the cost of which edges we select to create our spanning tree. So you saw this decision over here to convert this graph to a spanning tree by removing an edge. But we could have created a spanning tree by removing this edge, or this edge, or this edge. And the decision on which edge to remove can impact whether we end up with a minimum spanning tree. And so the requirements are here, right? We have all the vertices connected to acyclic, but the edges whose weights have a smaller sum than any other spanning tree form this spanning tree. We've selected the lowest possible collection of edges to create this tree. So let's look at some examples over here. In this case, we got rid of the 8, but that wasn't the best choice because we could have gotten rid of the 16, right? This cycle could have been broken by removing a more expensive edge weight. So we get rid of the 16, we end up with the actual MST right here. So there are many ways, there are multiple ways, there are 2 ways that we're going to look at for actually finding an MST from a graph, and one of them is Prim's algorithm. It's a greedy algorithm, which means that we're going to be picking the next best option in every iteration without having to worry about all the consequences of picking that option. And so we're going to separate our vertices into 2 groups, innies and outies, nothing to do with belly buttons, everything to do with graphs. We'll look at an algorithmic implementation or approach to this, but let me just show you a visualization of what's going on in Prims before we get to that. So we have this idea of innie vertices and these pink outie ones, and every step we're trying to absorb vertices into this inside kind of a spanning tree. So we're going to decide which ones we're going to kind of draw into the blue, and we're going to slowly build up a spanning tree until we have the minimum spanning tree. So this is an intermediate step of our Prim's algorithm, and every step we're going to find the closest out vertex x. In this case, let's treat the length of an edge to be the actual weight. Let's just say the numbers correspond that way. In this case, we would pick this edge to be the next edge, the next vertex to be added. Okay, now that we've done that, the next step is to mark it as in. So okay, it's marked as in, and we're going to update everything that vertex, this vertex right here, introduces. This introduces an edge that we never had explored before. We also introduce this edge. And by introducing an edge like this, we have another way to get to this vertex right here. So this vertex could have been reached from here to here, but you'll notice that we have a better edge weight right here. So this is better, it's a better weight because it's a shorter connection. So we're going to, in the data structure that I'll discuss in a moment, we're going to forget about this connection here, and we're going to think about this connection moving forward. We're going to consider this edge weight because it's a better way to connect this. Remember, the goal is to pick the lowest edge weights that create a spanning tree. Because if we have those lowest edge weights, we're optimizing for the lowest total cost. So we repeat this process of kind of absorbing entries one by one until we have no more out vertices. So here are the steps again. We can start by just selecting a random node and marking it as an innie. So if we just start with any node, let's look at this example over here. We're going to start with V1. So you might store a table like this with a bunch of vectors. One vector might include these booleans right here, which tell you whether a node is innie or outie. So if it's true, that means it's become part of our MST, inside the MST. We also have another vector that tells us how far it is, how far that vector is from the nearest innie. This value stays at infinity if we haven't been able to discover it yet. So let's say we're at V1. V6 is not something that has been approached yet because we don't have a vertex that has an edge with it yet. So it's going to stay at infinity. And we also want to remember which vertex could have gotten us this edge distance, the best one so far. So in this case, we're going to start with V1. And we're going to set its distance to 0 because it doesn't really make sense to give it a value. You could just say 0 represents that this is where we start. So once we've added V1, we have now incorporated it into our MST, and we have new edges that we can consider. So we have this edge over here to V2 and this edge right here to V4. And we're going to update our table so that eventually, when we decide to add the next vertex, right, this step, in one step, we only add one vertex at a time. right? So in the next iteration, we might want to look back and remember that we discovered these edges. And we're going to say that V2's index, maybe every vertex will have its own index. So index 1 will give you the entry in this vector or this vector or this vector that corresponds with V2. We're going to say that its shortest distance, the best way to get to it, is an edge weight of 13 from V1. And we're going to do the same for V4 coming from V1 with a weight of 7. All right, so once we've done that, we're going to pick the lowest edge weight from this column for things that haven't been absorbed. So again, I'll say that again. Things that are still false, that haven't become innies, or these are outies, we're going to go through and pick the one with the smallest edge weight. So the one with the smallest edge weight was this V4. It now becomes true since it's inside our MST. So we've absorbed it, we've added this edge, these are now connected, and we have to update new edges now. We have new possibilities to get to other vertices. So we're going to update the entry for V5, for V6, and V3. And so we've done that right here, here, and here. And we say that they could come from V4. All right, the next step over here, the V6 had the lowest edge weight for the things that were next to innies. And so we're going to add that. This doesn't introduce any new edge weights, so nothing to update here other than the fact that it's now inside the MST. And then the next lowest edge weight is this V5. So when we add the V5 right here, we'll notice something interesting. We now have another way to get to V2. So this edge weight of 5 is better than what we previously had here. Remember when we started with V1, we said that you could get to V2 from this edge over here. But we don't care about that edge weight. It used to be 13 V1. We don't care about that anymore because we have a better way to get to V2. And again, we're trying to get the lowest total edge weight in our MST. And so when we forget this information, replace it with 5 and V5, we allow the opportunity to continuously update the best so far for V2. And so in the next iteration, you'll see that V2 is absorbed through this edge weight right here. So far, this is what our MST looks like. And the last step, you'll see 6 is going to be the lower edge weight. So that's how it's going to be connected right here. So that's the formation. This is our MST. How do we end up getting this, or how do we spit out this result? This table at the end, once we're done, it tells us what the connections are, right? So if I want to know what V2 is connected to, V2 is connected to V5, V3 is connected to V4, V4 is connected to V1 with a weight of 7, and so on. And so this final state of our Prim's algorithm tells us what the actual MST is. So there are some complexities involved with Prim's algorithm. If we have an adjacency matrix as a graph and a linear search to find the next vertex to add, that means that we have a matrix that looks like this. Let's say there are 4 vertices. And every time I want to look at V1's adjacent vertices, let's say I'm looking at V1, just like this example over here, and I want to find which things are connected to it so I can actually check the edge weights. And each entry in here would be like, maybe this would be a 3, and this is an edge weight of 2. This is an edge weight of 5, right? This tells us 0, 1, 2, 3. This tells us that the edge weight between V1 and this vertex is 5. And so linear search would mean going through each row for a vertex one by one, right? That's our linear search. And so that ends up being V squared because we're doing something for every vertex. So it's V times V. Since we're doing for every vertex, we're doing a linear search. With an adjacency list as a graph, remember our adjacency list looks something like this, with just the minimum number of vertices for every vertex depending on what it's connected to. We end up with a different runtime. If we use a binary heap to look up what the lowest edge weights to add this vector are, this is how we're going to come up with this complexity. So we have E log V. Log V comes from operations on our binary heap. So let's see, how do we decompose this? So V log V plus E log V is what this is essentially equal to, right? And E log V comes from if we discover a point in our MST or in our graph where we have to consider a new edge weight. Remember how we updated entries in our table? This would be updating our binary heap. And that would mean calling update else E times. Right, so log V times E, because there are E many edges and we might have to update for every edge that we end up discovering. Remember when we updated the table. And then we have V log V, right, this component over here, and this comes from actually adding in new entries in our heap, right? So if we discover a new vertex, right, we go from here and we've discovered this vertex and this vertex, we're going to add this vertex as an entry in our binary heap, and so that's V log V. Remember, this is like a bottom up fixed down, or not a bottom up fixed down. It's like a insert into a heap, which has n log n runtime. And so we can actually simplify this. You'll see right here, we actually end up with E log V. Why is that? Well, we know that the most number of edges we could have is about V squared. And if we have E is about equal to V squared, then this term right here is kind of dwarfed by the E. And the minimum number of edges we can have, right, if we want to have everything connected, well, look, I mean, here's a graph. There are about V minus 1 edges minimum. So it ends up being simplified down to this because of log rules. Or because of the nature of E and what it could be with a sparse or dense graph. All right, so what if we have an adjacency list and we use a Fibonacci heap? The special thing about a Fibonacci heap is that we have amortized update elt, so O of 1 amortized update elt, which means that we don't have this term over here, E log V. We end up with V log V. The E over here comes from, I believe it comes from having to traverse over the edges in an adjacency list. But yeah, so these are the runtimes to be aware of with Prim's algorithm. So let's talk about Kruskal's algorithm now. It's another way to find an MST, but with a different kind of philosophy. It's also a greedy approach. We're making local best decisions, but we're maintaining a forest, a collection of trees that are disjoint. And eventually, as we add them up together, we'll end up with an actual MST. So we're going to iteratively select the cheapest edge in the graph. And we can continue picking the cheapest edge as long as we don't create cycles. And this is best for sparse graphs. So let's see how this would work in action. Here's an example of a tree. And our process is going to involve picking the lowest edge weight as long as that edge does not create a cycle. So we're going to add the 2. And we're going to throw all these vertices, all these edges are going to go into a heap of some sort, something to, we can sort them. We could put them into a heap. Best to sort them in this case because we're not going to update the edges. We'll sort them. We'll have maybe 2, 6, or 2, 4, 6. Oh, keep messing that up. 5, 6, 7, and so on. And so we would pick the 2, and then the next lowest edge would be this 4. Still no cycles created. Then this 5. Right? These are now part of their own tree. We call this a forest because this is a tree here. And this is a tree here. They're their own trees. Oh, wow, it's creating a forest. Very cool. And then the next lowest edge that we can add is this 6. Okay, still no cycles created. And then we have 7. If we get 7, we have a way to go from V2 to V3 to V4, then back to V2. This is a cycle. We cannot have this. So what we do we go through some complex situation? No, we don't. We just go through our Kruskal's algorithm, skipping this edge. So this edge is not going to be considered because it introduces a cycle. And then we continue on from there. 13 gets absorbed into this tree. Really, it's all one tree now, and we end up with this as our MST, like so. So to actually run this algorithm, we'll sort the edges by weight, right? This is just like n log n with merge sort, for example, you get E log E time. We use the disjoint set data structure, right? When we used union find, that's what we're talking about here, to keep track of the vertices in each component. So what does that mean? What are the components here? Why do we have to use union find again? How is this relevant? So again, the important step that that makes Kruskal's algorithm a little complicated is making sure that we don't have cycles. How do we know that introducing this edge introduces a cycle? Well, remember that every edge, this edge over here, is essentially a pair V2, V4. Wouldn't it be great if I could know that V2 is part of the same tree as V4? So one way to do this is to just remember, is to just look at V2 and check every single thing is connected to V2. Does V2 go to V3, then V4? Does V2 eventually connect to V4? If V2 is already connected to V4 indirectly, then that means that creating this edge would create a cycle. So we have a fast way to do that. Remember, we used union find to check. Here's one person, and here's another person. We wanted to check whether they have a king that they share. So this is essentially what we're doing. We're trying to decide, do these people share a king or share a leader? So when I want to introduce this edge, E of x, I ask, find V2, are you equal to find V4? If this is true, then we would be creating a cycle. And we would decide not to add. Do not add. So that's where our union find data structure would be useful. We're able to check whether things are part of a component, the same component, if they're part of the same group. And every time we absorb or add in a new vertex, we're going to update its group to know that it's now part of it. So now its representative is going to be the representative of V2 when we add in V1, for example. So the total time complexity we end up with from Kruskal's algorithm is just coming from the sorting of the edges. And you'll notice here we have an equivalence here, E log E and E log V, and that's because a log of V squared, and we said that V squared is the greatest that E could be, right? E is less than or equal to V squared. A dense graph means it's about equal to V squared. Log of V squared is equal to 2 log V, just with log rules, because the exponent ends up going out as a coefficient. And constants are dropped in our big O, right? So this gets reduced to E log V because of log rules. And so you'll see we have the same time complexity with Kruskal's algorithm. Faster in practice though, but same time complexity with Prim's binary heap for sparse graphs specifically. So now that we've talked about MSTs and how we identify them, let's talk about updating our graph and making sure that we always have an MST. So here are different situations in which you would have to modify the MST, or maybe not modify them, but consider whether you need to modify them. So let's say we have an edge in the MST and we're decreasing its weight. So here's this edge right here, edge 8. It's already part of the MST. We ran Kruskal's or Prims. We just want to determine that whether updating this edge weight is potentially going to change the correctness of our MST. So if this 8 becomes a 3, we're actually just as confident that this is a correct MST, because lowering an edge weight is actually better for us. Remember, we tried to pick edge weights to minimize the cost. If the cost for our current MST is even lower, then nothing needs to be done. We don't have to introduce a new edge and get rid of this one, for example. It's a good edge. It's just as good as it was before. Now, what if the edge is not in the MST and we're decreasing its weight? So if we try to change this edge weight, which is not part of the MST, that's why it's grayed out. If we lower its edge weight to 1, we actually have a better way to connect this group over here to this group over here, right? The only thing binding this group here and this group here is 8. And if we have a better way to connect them with 9, we'd be able to actually improve our MST. And it would actually become an incorrect MST if this becomes a 1 and we don't update it. So what do? We replace that edge with the new edge because we know that this edge forms a connection between these two between these two groups. Now, what if the edge is not in the MST and we're decreasing its weight? How do we actually like do this step? Because it's not that simple, right? You have to actually determine which edges we have to remove or add. You can't just decide, okay, I'm just going to cut off some random edge. You have to determine which edge is the one that's going to be removed. Because remember, in this context, I'm just telling you, here's an edge, I'm going to reduce its weight. You have to figure out what components are we disconnecting from each other and to determine which edge we're going to remove. So we're going to add the edge whose weight was decreased to the MST. Now we have a cycle. So the one that we added was this one right here. And we're going to remove an edge in this cycle that has the highest weight. So remember, a cycle could be 4 entries, could be 4 vertices. We're going to have to go through and find the one with the highest weight. And we can do this with BFS or DFS. We just need to make sure that they are part of this cycle. Okay, and here's another situation, part 3. If the edge is not in the MST and we're decreasing its weight, then that means that, increasing the weight, then that means that it's even less useful of an edge, right? So if this edge over here becomes 1 million, then we're even more sure that we don't want this edge because, again, we're trying to minimize the edge weights. What if the edge is in the MST and we're increasing its weight? So there's 8 over here. If we raise it to 11, we might have an edge that is better than this 8 now. So how do we determine which edges are involved in reconnecting this group to this group? So we raised it to 11, and we need to find a new MST. To do that, we're going to remove this edge. Right, we're going to break this edge, and we're going to consider all of these edges highlighted in blue. How do we determine which of these edges are part of the blue highlighted group? Well, if you take a look at this graph for a bit, you'll notice a pattern. It seems that these blue lines are kind of like a bridge between this area over here and this area over here. And that has to do with union find. These are all part of one group. Maybe their leader is 8, or this vertex rather. And this is another group, and their leader is this vertex. I can traverse the graph and ask every edge, is your leader, right? I'll look at the 9, for example. I'll ask its left edge, or its left vertex, and its right vertex. Is your leader not equal to this one's leader? If they have different leaders, let's say this is A and this is B. If this has leader A and this has leader B, then that means that they are separate, right? They're not equal leaders, which means they're separate, which means that adding this edge would connect things that are not part of a union, that have not been unioned. So now we know that this is one of the possible edges. Now we consider the 9. Do the vertices that you're connected to give us different leaders? Are they part of different connected components? And so that would return true. If we look at the 2, if we look at this 2, for example, as we're iterating through our vertices, we would find that these 2 vertices have the same leader, so it's not useful. This is not an edge that we were introducing, and already it's an edge that we have already included in our MST. So that's another reason why we would not be considering it. But for example, this edge over here is not worth consideration because both of its vertices do not have different parents. And so here are our edges. We just pick the one with the lowest weight. In this case, there are multiple with the same weight, and so any of them would be valid in selecting which edge we're going to use. So you can find the new edge to add an O of E time. We're looking at all of the edges, and we're quickly checking with union find, which O of 1, which gives us O of 1 time per edge for hash lookups. Or rather, just for union find, you get the Ackermann function, which reduces to O of 1. And yeah, it's O of E time to actually update this MST. All right, now on to the handwritten problem. So given an undirected connected graph, check if the graph contains a cycle. So a connected graph again means that every vertex has some edge to it, and all of the edges end up creating one like graph, right? We don't have like separate graphs. So like this is an example of an undirected connected graph. We want to determine whether this graph has a cycle. So feel free to use a helper function. And there's an assumption coming with this adjacency list, this vector of vectors, such that if u and v are adjacent, then the adjacency list at index u for entry u will contain v, and the adjacency list for v will contain u. And there's no reflexive property where u is contained within itself. So, for example, let's say we have, let's look at an example here. We might have our vertex, let's represent it as, let's say this is our vertex that we index in. So this is, let's redraw that. So this is adjacency list. This is the outer adjacency vector, and this is the inner adjacency list vector. And again, this is an adjacency list, so each vector only has to be as large as it needs to be. So if this vertex here is only connected to one item, like v5, then we would only have v5 here. So because of these rules, if we have let's see here. Let's say this is the adjacency list for v2. We're not going to have v2 in its adjacency list. If it has a connection to v3 and v5, we are assured that v3 also will store v2. Right? So there's this relationship that's held in both vectors. Right, and they don't have to come in a particular order, I guess. I don't think there's a rule on the order of the vertices, so you do have to check every entry in the adjacency list. The complexity should be O of v plus e time. Yeah, best of luck. Thanks for tuning in, and please ask us questions on Piazza or in office hours if you have any questions or concerns. Thank you. Bye.